computer. Okay, so now finally let's get to the science situation. So today we'll be just looking at the last chapter. We kind of started looking at that. We, I think, covered like one slide maybe of this chapter, and then it says about amines and amides. So we'll try to kind of like take a look at the most sort of like fundamental important things for both classes of compounds, such as we'll take a look at the functional groups, right? And then some chemical properties. That's where we need to be most importantly. And so maybe some physical properties, right? And then like such as hydrogen bonding, which is what we can like imagine would happen in those compounds because they have something in common, right? So if you just recall the functional groups, which we have been exposed to from the beginning of the semester. So some people have been recognizing those photos quite, recognizing those functional groups quite nicely on the exams, right? So that's the amine, that's the amide, that's some sort of like ester versus ether, right? So things like that. So at this point, we hopefully remember what amines and amides are, right? And then what they have in common, right? So now let's take a look at the questions that have been asked. So it's about your expectations for after this. So because now we have the last presentation and penultimate day of classes broadly. So let's see what people think. So lots of people are going to recover, looks like, or they say yes. All right, so recovery and yes is kind of the prevalent answer, and some people are going to work in the summer, so it's kind of like a mixed situation. Yes, I don't know what yes means, but okay. So yes, lots of yeses, and then some people are going to work and they recover. All right, so and semester went well. Okay, good. So at least for some people, well, so like we have the overall positive tendency to move on. All right, so now let's take a look at what's happening with the amines, right? So if we look at the amines versus amides, so let's just think about another question in the Google Classroom. Right, so the question will be like that. So what do amines and amides have in common? So it's going to be like a broad question, so to speak, but maybe it will help start the kind of like activities of today, right? So, and then that's where we are. We're moving to activity number 1 already, or activity 0. Rather, so what about amines and amides? What do they have in common, right? So just think about that. So now we're going to take a look at some kind of structures, right? So like amines, they look like that. So previously, so if I start drawing here, so we're talking about the general chemistry, of course, right? So such as NH3. So that is like part of the general chemistry courses, right? So that was ammonia. So and then, so here we can see how this structure is connected, for example, to that one, right? So if again you recall question number 1 from exam 1, or like one of the questions from the first exam, so we were like, okay, well, how do we make, for example, cyclohexane from hexane, right? And people are saying, well, you just need to remove like H and H from the end terminal carbons and connect the CH2 and CH2 together, so they will make like a single bond between 2 carbons, right? So it's going to be pretty good. So same thing happens here. So if you think about it, you have those covalent bonds. Each covalent bond is made of 2 electrons, right? That's why there was a question on the exam about that. So that's like for your kind of like handling of this information, right? So here you can theoretically somehow disconnect or break those bonds, right? And you will have those like free electrons here, like 1, 2, 3, 3 free electrons, right? So then they can theoretically be connected to, for example, I don't know, maybe 1 methyl group, right? So you can do that. So granted that methyl group has this kind of carbon with a free available electron, and then you can move on after the combination, right, of those 2 things. So you can move to something like this. So you'll have N. Let's imagine that we are going to leave a couple H's, right? So one of the atoms will be gone, and now you have the methyl instead of that. So that's how you can like make an amine. So just kind of like draw the bond here, and then you're all set. right? Of course, we must not forget the lone pair that remains. So that was like not touched yet, unless we start chemical reactions, which is what is going to be our next step, right? So sometime in the near future. So that's the amines. So and then yeah, that's how they're formed basically. So at least in our mind's eye, or so the saying goes. So you remove like H's consequently, and then you are going to switch them to some sort of alkyl chains, right? So here we have pretty simple ones, such as methyls, right? So, but of course, as we can imagine, we can have something more complicated quite easily, right? So then here's an example, right, of more complicated amines right away. So, and it shouldn't be a big deal. So because we saw all those parts, right, previously, and now we just combine them into something new, such as some kind of like crazy looking amine, right? So maybe it's going to be like that. So it's almost like NH3, but without one hydrogen. And now I'm going to kind of like make this available electron for the bonding, right? So, and then I can put down something like that, right? So because why not? It's going to be some kind of like huge alkyl chain. So maybe even with let's do like a phenyl ring at the end as well here. And then here you go, right? So it kind of resembles our worksheet activities, which are kind of like similar to exam questions to some extent, right? So here you go, that's your amine, right? So here you have alkyl chain, then you have the aromatic ring. So all the like familiar things, and now they're kind of like combined into the new compound. So that could be like the case. It is going to be some kind of like aromatic amine, right? That's what you can call this compound because it combines all those like functional groups, right? And of course it has the like alkane character as well. So like with a bunch of carbons. So that's your amine. So now about classes of amines, right? So we have primary, secondary, tertiary. So this is just kind of like the thing about the substitution, right? So if you start with, let's say, ammonia, so you can imagine that like in your mind at this point. So primary amines happen when you switch one H of the ammonia to some kind of like alkyl chain, right? And then here you go, right? So you have this RNH2, such as, for example, methylamine, right? So that's how you name it, by the way, right? So we'll typically be using the word amine to name them, and then this word will be preceded by the name of the substituent and their number, right? If that is the case. So, for example, if we switch out just one H in the previous like ammonia to, for example, methyl as our alkyl chain, like one carbon chain, right? So we're going to have the methyl amine. So like pretty straightforward, right? So like you just need to know what the amine is, right? And then methyl, okay, well, that's also something that should be remembered at this point, right? So methylamine is formed. So it's going to be the primary amine. So because we only like basically remove one H from the original ammonia, if ammonia is the predecessor of amines, right? So that's like what we need to think about. So then what else? So now we have some other examples of primary amines. Let's do that. So maybe we'll have like a NH2, right? So that's going to be our prerequisite. So then it's going to be like one bond available to bind with some sort of alkyl chain, right? So that's also a primary amine. So, but instead of methyl, you have something else. You have 1, 2, 3, 4, 5. You have here, that's a bond right there, right, to the carbon. So carbons are going to be in a salad green, right? So these are your carbons. So now we can count how many 5 green dots, right, in this diagram. So that's going to be what? Pentyl, right? So if it's 5, it is like going to be the root will be pentane or from pentane, pent rather. So pentyl amine, right? So again, that's the name of the alkyl substituent, right? So we have methyl from methane, so we have ethyl from ethane, and so on. So pentyl, it's from pentane, so pentyl amine. So that's your amine, right? And this is going to be a primary amine as well because we only remove like one H remove one H, you have primary, right? So they kind of like are congruent with one another. So then we have the secondary amines, right? So maybe we can do something different, more exciting from the slides, right? So in this case, you can think about, okay, what's secondary, right? So that's when we switch out two hydrogen atoms in the original predecessor ammonia, right? So this will be looking like this. So we are going to have like N with the lone pair, of course. Then we're going to have here H, right? So one H will be left over. And now we're going to have two free electrons with some sort of groups. Let's maybe make it aromatic right away, right? So because this is, again, familiar stuff already. And I'm just going to show that like this. Okay, so this is going to be our secondary amine, right? So that's what it looks like. And then in this case, we're going to have the groups, right? So we have the word amine at the end for our nomenclature skills. So this is a phenyl. Phenyl and phenyl. There are two of them, and typically people say, well, it's going to be diphenyl, right? So di stands for two. What? Two phenyls. Diphenyl amine. So this is your secondary amine example, right? Already with aromatic rings. So finally, tertiary amines. So let's move on. So in that case, yeah, you again can guess educatedly that you are going to switch out all the H's to something else, right? So in your original ammonia as a kind of like precursor, as they say in like medicine and such, right? So here you can have like, for example, try, let's make it maybe a little bit a longer chain, right? So maybe like this. So that and that. Okay, so that's the one, right? So this is going to be triethyl amine, so which is going to be a very common compound. So you have here your ethyl three times, right? So that's your two carbons. That's a carbon-nitrogen bond here. So that's not a carbon. It just goes straight to the nitrogen, you need to imagine, right? So like this and that. So and then I can maybe like prolong it a little bit and then make it like so. All right. So these are your carbons and nitrogens, right, in this particular amine. So, and then we have here three ethyls, right? So we're going to use the prefix triethyl amine. So this is going to be like a very common compound. It smells like fish, and then it can be used a lot in organic chemistry, right? Especially in synthesis. Maybe it's used somewhere in medicine as well. So who knows? So, but yeah, this is going to be just like a common thing, right? So triethyl amine. So just be aware. Hopefully it's a good example. So now we are moving on to further things, right? So like in terms of nomenclature. So yeah, I think typically we'll be looking at like there are two ways to name them, right? So either when you attach substituents to the central nitrogen carbon, I mean to the central nitrogen atom, right? And then you name it. So you start with substituents and then you finish with the word amine. So then what else? We also can have some like a little bit like different names, right? So here, what do they say? So in other cases, they can start with the alkane, right, as the main chain, so to speak, from which the name will be built, right? So here we have two propane amine. So like, how does that happen, right? So for example, here in this case, we are going to have our propane. So because we have three carbons total, right? So, and then looks like position two, carbon two, will have the amino group NH2. So that's how the naming works, right? So two propane amines. So that's one way to name it, right? So also, if you look at this substituent, right? So this substituent here with the yellow carbons, it is nothing more than isopropyl, right? So theoretically, you can also call it isopropyl amine, right? So that's going to be also fine. So then what else? So we have like cyclo things. We didn't really look at the naming of them, so we just need to like know that they exist, right? So then what else? You can also have amines with two functional groups, right? So in this case, you are going to have, again, 1,6-hexane diamine, right? So in this situation, we are going to use hexane as the root, right? So it's going to be basically the alkane name. So since we are going to have here, we observe 6 carbons, like 6 green dots. So, and then apparently positions 1 and 6, right? So positions 1 and 6 will include the 2 amino groups total, right? So that's how the connection works out here. So, but for our intents and purposes, in the interest of time, we'll be just looking at the very like simple nomenclature, and it's going to be basically like it will boil down to some kind of substitute analogs of substituted ammonia, right? So, or derivatives of ammonia, let's put it this way. Because this one, so if you look at all our examples, which you have doodled so far on papers, so they all derive from ammonia, if you think about it, by switching some number of hydrogen atoms in ammonia to something kind of like alkyl chains of some sort. So then we also have our common amines. So this is going to be kind of like a must know from the aromatic real. So this one is aniline, right? So it's also an amine if you think about it, also looking at your previous experience, right? So, and then we also will have a bunch of substituted anilines. So because those compounds are like very popular, maybe you will encounter them somewhere else in the future. So, and then here we go, right? So speaking of nomenclature of anilines, so here you just need to like see that you have this like aniline piece here, like in the red circles, right? So, and then naturally, your name will include the word aniline for all those compounds, right? So then before aniline, you need to like show the substituents and their position, right? So number again stands for the position of the substituent followed by its name. So in this case, for nitroaniline, why is that so? Because so carbon where nitrogen for the amino group is attached is going to be carbon number 1, right? So that's the carbon-nitrogen bond. So carbon will be numbered as number 1. So this is going to be also carbon number 1 here. So then you count and then minimize the numbers, right, for the substituent position. So here, no matter how you go, you're going to obtain NO2 in position number 4, right? So let's put number 4 here, and then you will have 4 nitroaniline. So NO2 is not the same as NH2. So just pay attention to those details, right? And then kind of like we need to remember that there is a difference between nitro and amino groups, quite substantial, right? So then here you have 4 nitroaniline. So if you count the position for the methyl group right here, so you can go both ways, so but you'll get different numbers. So if let's say we go counterclockwise, we're going to be like 1, 2, 3, 4, 5. Pretty high number, right? So but if we go clockwise, we go 1, 2, 3. So in that case, it's going to be position number 3, which will feature your methyl, right? So you will have 3 methyl aniline. You are going to minimize the number, right, of the substituent. So yeah, that's it. That's going to be your substituted anilines. So that's kind of as far as we go nomenclature wise for like our final exam where amines will be featured. Okay, great. So now let's move on further. So what else do we have here? So we can potentially, okay, so common names. All right, so let's see where we are. So yeah, that's another way like to name amines, right? So that's going to be like a special case, but it happens to be like in nature, right, in chemistry. So here you see aniline, right? So why is that so? I'm just going to circle this piece, right? And then this like red area looks almost like aniline. Why is it almost? Because it's 1 hydrogen short on the nitrogen atom, right? So if it were aniline, it should have been your phenyl ring with NH2, right? But here we have phenyl ring NH, right? So it's kind of like almost like aniline. And then we have the substitution, right? So like this yellow methyl was kind of like attached to the nitrogen instead of the hydrogen, right, in the aniline. And now like we have this like special nomenclature thing, right? So which says N. So N stands for the fact that the methyl is on the nitrogen here, right? In this particular example. So we have N-methyl aniline. So if you see N, not the number, right, then you are going to say, aha, okay, so it means that the methyl is supposed to be on the nitrogen, right? So you imagine aniline with its original structure, which is going to be what? Which is going to be C6H5NH2, right? So you have something like that. So that's your original aniline. You just kind of like draw it for your practice purposes. And then if it says the N, let's make it like maybe N isopropyl aniline, right? So how is that going to work out? Well, quite easy. So we're just going to remove H, right, from aniline. And then if I want to draw N isopropyl aniline, I'm just saying that, right? So it's going to be looking like this. So we will take a look at our like aniline structure, and then the name goes like that, N isopropyl, right? So you have N, H here, double dot for the lone pair, and isopropyl, right? So let's show the isopropyl. It's going to be like that. So that's the one, N isopropyl aniline. So this is our isopropyl, right? So this is carbon nitrogen bond right here. So 3 carbons, all good. And then you have N isopropyl, aniline, isopropyl, aniline. So that's kind of like another way to go about naming amines. So if we have 2 methyls somehow, right? So we can show it with N, comma N designation, and N dimethyl. So di stands for 2 methyls, and then they are both kind of like methyl, methyl. So on nitrogen, right? So that's why we have N, comma N piece there, and N-dimethyl cyclopentanamine, right? So why is it cyclopentane? So because, again, we can spot the cyclopentane amine originally in this yellow circle, and it's going to be cyclopentane. So this is just going to be 5 carbons in a cycle, right? Cyclopentane. So cyclopentane amine used to be like this, right? So you have substitution, 1H is switched to the NH2 group here, cyclopentane amine. So yeah, that's where we are in terms of nomenclature. So this is just some kind of like more examples, right, that we can potentially have, right? And now we are going to, let's get to the properties, right? Because we want to cover the chemical reactions, most importantly of the amines. Right. So, and in terms of the amines, what do we need to know for the chemical reactions, right? So, first of all, let's start with the hydrogen bonding, right? So, like we are going to take a look at the physical properties prior to the chemical ones. So, what do we have here? So, there was a question in the Google Classroom, right? So, like, what do amines and amides have in common? So some people answered, good job. So they were basically saying they have nitrogen atoms, right? So nitrogen atoms are everywhere. So they're both organic compounds. That's good. So they have the N bond, right? So, but what is more, if you look at the amines and amides, they both have the NH kind of like bond, right? So which is going to be the prerequisite for the hydrogen bonding, right? So now we can have it in amines, apparently. So because why? Because we have the famous NH bond, which is kind of polar, right? So because there is going to be the substantial difference in electronegativities between H and nitrogen, right? So there's going to be like a jump in electronegativity difference if you look at CH versus NH bond. So CH bond is considered non-polar, as we like know from the beginning of this course, right? So that's why, for example, alkanes are non-polar compounds because they have like non-polar bonds essentially everywhere, right? So, but if you look at amines, they will have this highly polar NH bond. So that's number one. And number two, so it can participate in hydrogen bonding, right? So you can kind of like make a letter or like whatever it is, like levels of your knowledge this way, right? So that's one of those examples. So we have different electronegativities, right? So that's kind of substantial. What can it lead to? It can lead to this kind of like formation of the special bonds, such as like NH, right? So, and then it will lead in turn to I mean, hydrogen bond formation, right? So we can show it this way. Maybe we have like couple of pentyls here, right? 1, 2, 3, 4, 5. So then another chain also with 5 carbons. So that's like all good here. So then we're going to show the kind of like the lone pair. And now we are going to show our partial charges, right? That's the next level in the knowledge. You have delta plus on the hydrogen, delta minus on the nitrogen, because nitrogen is more electronegative, that tends to draw electrons to itself. So consequently, we will give this atom delta minus, and then H will be delta plus, because it tends to kind of like lose its electron, right, along the line of this bonding. So then we can show the, for example, hydrogen bonding between those two amines, right? So you can do that. So just show kind of like align your minus and pluses, right? Partial charges. So you have here delta plus somewhere at kind of like the same molecule of this amine. So you have 1, 2, 3, 4, 5 carbons. And then you have here again 5 carbons. So that's it. And now you can show your hydrogen bonding, right? So delta minus, delta plus. So this will be just kind of like with the dotted line, so which will stand for the hydrogen bonding, right? So you can also kind of like throw in water in the mix, right? So it's also possible. So because like amines are kind of like not completely, what's it, let's say, if you let it be, right? So in the jar or in the what a beaker, let's say, in more professional chemical terms, then if you imagine the water molecule flying around somewhere, so what's going to happen, right? So you have this like HOH. So from the air, for example, so then the amines will tend to absorb water because they can form quite strong hydrogen bonding, right? So hydrogen bonding is kind of like pretty strong interaction between molecules, right? On the kind of like a larger level. So, and here we go. So we can like think about, okay, delta minus on the water, right? On the oxygen, delta plus here. And now we can form the bonding, right? So maybe it's going to be like this. So we have delta minus, delta plus. And then we also have the hydrogen bond between the H of the amine and oxygen on the water. So now you can see, so even if you kind of like show like 3 molecules here, you can already form a lot of potential hydrogen bonds, right? So that's why amines tend to absorb water from the like ambient environment if they just kind of like let's stand right on the bench top somewhere. So yeah, just kind of like some conclusions to like think about, right? So and that's how you can like draw the hydrogen bonding between not only amines but also some like other molecules. So then what else? So boiling points, that's just like mostly for statistics, I would say, right? So here we can notice some trends. So if we like take a look at, for example, amines, right? So here we can see some sort of like tendency, right? So let's say we go from like primary to secondary amine to the tertiary amine, and looks like the boiling point just goes down, right? So then you can think about how the structure is kind of like linear versus branched, right? So this amine on the left side is very linear, right? It's just like 4 atoms in a row. So then this secondary amine is a little bit more branched. So we can argue that it is branched because we have the ethyl and methyl branch stemming from the nitrogen atom. And then this one is the most branched, right? So, and then the more branched your compound is, right? So the less like packing type interaction there is between the molecules of that compound. And then consequently, it's going to be easier to boil it, right? So that's where we kind of like will stand, right? And yeah, that's like pretty much like what we can say about the boiling points of the amines, right? So here, just one trend, right? So branched versus linear structures. So what does it lead to, right, in terms of the boiling points? So now that's just a table for like some like more stats, right, for us to take a look at. So here we have the boiling points, and then if we look at the increase in the molecular weight, which is what we observe as we go from the very light amine to some sort of like huge amine here, then the boiling point will tend to go up, right? So, and here we go. So it's going to be like easier, I mean, more difficult to vaporize the molecule, which is kind of huge versus the molecule, which is small. So, now we are going to kind of like, yeah, this is some more examples of the hydrogen bonding that can exist, right, between various classes of amines and the water molecules, for example. So that's just kind of a little bit of the like additional material or like general examples rather to what we have on the drawing on paper, right? So here, the common thing that you are going to notice is that if I look at the middle example, for instance, there is going to be delta minus on the nitrogen and delta plus on the hydrogen, right? So that's like pretty good. If I look at this kind of like rightmost example, same thing. So delta minus, delta plus. So you see, so since according to physics, right? So like opposite charges will attract. So that's how you are going to align those molecules when you draw them on your own as you review, like in the library or like somehow else, right? So if you look here, for instance, right, what else do we have? So like we can see, okay, well, there is like a delta plus on the nitrogen, I mean, on the hydrogen, and there is a delta minus on the oxygen of the water. They can also kind of like be aligned that way. That's okay. So maybe you'll also have some connection, yes, between the hydrogen, right, of the water. So that's fine, delta plus, and nitrogen of the amine because it's delta minus. So they can be kind of like put together next to like one another. So that's fine because the opposite charges will attract. I guess just don't kind of like align nitrogen with oxygen because they will repel, right? So that will not make kind of like much sense for a hydrogen bond in drawing. So, but kind of like go with the kind of like physics premise, right? So, but again, you need to know who is delta plus, who is delta minus. Bless you. So then what else? So now we are going to get to the chemical properties. So that's going to be pretty much the pinnacle for today. So here we go. So this is going to be, what do we call it, right? It's going to be the proton transfer. So because in this case, we're going to transfer the proton from one molecule to another, right? What is the proton? This is the H plus particle. So previously we were looking at how the amines can accept the proton, right? So we're looking at a little bit like different case. So just as a refresher, so for example, we were also looking at the ammonia, right? How ammonia accepts H plus. So I will not be kind of doing this again. So because it's like Gen Chem, like fundamental prerequisite knowledge. But for amines, it's going to be like that. So let's make some, let's take a look at aniline, right? So because why not? So we can do that. So aniline used to be like this, right? So that's your just full molecule with the bonds, right? So I'm going to show it because it's going to be kind of important for the chemical reaction. So I can just give it H plus and I'll be here okay technically. So because why? So the slide says basicity, right? So what are the bases? Bases are compounds that will accept H plus. That's what I show here. Base accepts H plus, right? H plus is a proton, by the way. So now I'm going to engage this lone pair, and then it looks like nothing more than a bond in the future, right? So what do I mean by this? So let's kind of like show the arrows, and then we're going to make the bond in the future product, right? So that's going to be fine. So we are going to redraw lots of things, right? And now we're going to maybe notice that this bond used to be red, right? It's like red, two red dots. So now they are going to be spread out like so. And then one of those red dots will go to H plus, and then H plus all of a sudden becomes just the hydrogen atom. If I cover everything, so you're gonna see this like H with the dot, which is just the hydrogen atom at this point. So that's good, right? It's going to be neutral hydrogen atom. So then you are going to make the bond, right? So they just cannot be in the air, so to speak, right? And then you're going to notice something. So nitrogen used to be surrounded by 5 electrons of its outer shell that kind of participate either in bond formation or in lone pair formation, right? So, but now you're going to count the electrons, and then here we go. So we have now 4 electrons that surround nitrogen. So that's 4 electrons. So now the question to the audience here. So let's make it happen. So it's going to be kind of like crucial here, and then if you get past that, then it's going to be okay with like every other like reaction basically. So like why and what will the charge be on nitrogen, right? So that's going to be the question now to think about. And then it's going to be literally the same case applied everywhere, like for the basic behavior of amines, right? So it's like the principle which can be applied to lots of situations, right? So that's what we need like to think about. So like what's going to be the charge on the nitrogen and why, right? So in this final compound, so this is going to be our final compound that we make. So kind of like electrons are shared now, right? So you make a covalent bond, very good. So, but also something happens with the charges here. So total charge here is 0, by the way, so that's just going to be like a neutral molecule, right? Charge not shown, then it's supposed to be 0, so that's kind of the default setting, so to speak. So here, charge is shown because we want to make a difference, right? We want to say that we accept the product. If we don't show the charge on the H, right, it's going to be just the atom, right? So that will not make sense for our kind of considerations. You need to like make sure that you are on the all your ducks are in order or stuff like that, right? So, and then finally the charges, right? So you have the balance everywhere. You have like phenyl ring, nitrogen, 3 H's, phenyl ring, nitrogen, 3 H's on the left and right sides of the chemical reaction. So this is good. But now you have the kind of like charge situation to figure out with the nitrogen. So like what's happening there, right? And then why? All right, so let's see what we got. So like we have some effort going on. So thank you for that. All right. So like we have, all right. So like it's almost there. So we have, so H, yeah, there is an extra H, right? So, but it's going to be kind of the like ramification of why the charge becomes what it becomes, right? So, and some people say the charge is positive, right? So that's good. So the charge is positive. All right. So, but why is the charge positive? That's kind of like the problem, right? So, and the answer is that because you lose an electron, right? So, like one of those red electrons was lost by the nitrogen, and now it belongs to hydrogen. So now you have 1, 2, 3, 4. Only 4 electrons on the outer shell of nitrogen. So nitrogen atom lost 1 electron. Consequently, we must assign to that a positive charge, right? So now we're all set. So that's what I say, right? And try to show here. And now we'll have like a bunch, like more like practice examples to see this exact case, right? So then if you're able to explain it on the exam, well, it's good for you, right? So because this situation might as well happen in the future, especially if you kind of like continue with the like near chemistry things, right, in the future. So that is a like powerful concept, to be honest. All right, so the charge is positive because the electron was lost. All right, so that's all I was asking, right? So awesome job. So somebody did answer, at least one of your peers. Good job. You know who you are. All right, so now let's move on to what else? Okay, so these are some just more reactions, right? That's a little bit more advanced case. But here, same stuff will happen, right? Theoretically. So here, if you look at this, so let's maybe make them yellow, right? So those are yellow electrons and blue electrons, already kind of colorized. So very nice. So same thing will happen here. Your proton donor will be the water, because the water can be either acid or the base, depending on the situation in which it is participating, right? So here you are going to give the extra yellow electron to oxygen. That's what the like curved arrow shows. And now you are going to technically have those both yellow electrons here. These are yellow electrons. So now you can see that oxygen gets 1 more electron. He gets or like oxygen atom, it gets an extra electron. And now this kind of like electron, so it used to be on the hydrogen, now it is on the oxygen, right? So that's why, so you go from the neutral charge on the oxygen atom to the negative charge on the oxygen atom. So you're going to have the like negative charge right here. So because now it didn't lose an electron, it gained an electron, right? So that's like your like two-way thinking, right? Either loss or gain of electrons. So then what else do you have? So also like in the middle of the process, it's not shown here, but we showed it like on paper here. So we will also see the proton formation, right? So where does the proton come from? The proton comes from the water, right? So this guy, so underscored in blue, that's what becomes the proton, right? So it used to be the H with the dot, with the yellow dot, but then the yellow dot was gained, the electron, this yellow dot electron was gained by the oxygen. Consequently, the underscored in blue hydrogen had to lose one H. So what happens with the hydrogen atom if it loses one H? Well, you are going to go from H with the dot to, okay, like minus one electron, let's say, right? To you are going to gain, you're going to make a proton, right? So you're going to make H plus. And now exactly the same situation, right? So like it's not shown here in this kind of like process because it's kind of like assumed that like you have an idea how the H plus is formed from the water, right? So, and then you have this situation, right? Methylamine base reacts with H plus. So same exact case as here, right? And you are going to make your third bond, right? So you're gonna make a new bond between N and H. So, which is going to be composed of those like blue electrons. Blue electrons are now going to be here. So they will make the blue bond with the previous proton from water. So, and then you will have the positive charge on the nitrogen again. So that's the one. So yeah, things repeat themselves, right? So, and then you can also like do that exact situation with like any amine that you have, right? So if you see what participates in the chemical reaction itself. All right, so now we have finally, all right, so we have amine of your choice and base of some sort, right? So as a base, how would it react with water? Okay, so for activity one, let's maybe kind of like give way now to the people, and then we're going to look at some new compounds here, right? So for activity number one, I'm going to draw compounds, right? So which will participate in the process, and it's going to be like that. So first of all, we are going to have the secondary amine, which is going to be like this. Okay, so we have 1, 2, 3. So we have the H, and this one will react with the water molecule. So this is going to be our assisted activity number one. So that's part whatever, let's call it like part A, for example. So that's your amine. So it's a little bit different. So, but literally whatever is drawn here, those parts will not participate in the chemical reaction, right? So that's like good news. You just need to be able to redraw them. So you can give it a try. So like we have the first candidate. So let's go ahead and do that and see how it reacts with water. So if you noticed, so in neither of those cases so far, right? So the kind of like alkyl chain or the aromatic chain on the piece of paper was touched, right? It was just redrawn, to be honest. That's what we need to be able to do. So same will happen with those propyl chains, right? So don't be like scared of them, I guess. That's it. You just need to like redraw them. What will happen is like the lone pair, that's what will be kind of like participating in the chemical reaction directly, right? So great. So that's what you will have. And then you will have the side product, which is going to be OH minus. That's it, right? So that's literally all it is. So you can like push it down a little bit so that people can see. Yeah, that's it. So you engage the lone pair on the nitrogen from the amine, right? And then you broke the OH bond, or rather aniline be that thing, right? Aniline. All right, great. So that's all it is, right? So, and then it happened with the secondary amine. So good job. So now let's move on to another kind of like a random example, right? So maybe it's going to be, let's make it B, right? So like B, it's activity 1B. So I'm gonna now show the tertiary amine, so which is gonna be like this, right? So tertiary, and it will have the, let's make it three isopropyls, right? It's gonna be tri-isopropylamine, also reacts with water molecule, right? So that's going to be our next proton transfer, and we have, do we have the candidate? Okay, so like you can go ahead. So do that. So like we'll have some activities, hopefully a little bit more after that. So just use your chances whilst you can, since that's the last presentation. And that's what we got, right? So like what's happening here? So looks like people figured out that they don't have to touch those groups, right? Wherever they are, maybe like a phenyl or something like that, right? So the plus sign needs to be, however, not on the H anymore, right? So like, where is the plus sign? It's going to be on the nitrogen, right? So that's a crucial thing. So, and then that's it. So because H plus used to be H plus, it's somewhere on the left side, right? It's formed, and then H turns into the hydrogen atom, and you must have the N with the plus, right? So you can just remember that maybe like N has to be the plus charged, right, as a result of this transformation. So, or if you are a little bit more advanced, right? So if you just look in the details, not even advanced, then you will see that the nitrogen has to lose an electron, and that's what will explain you why you have the plus here, right, on the nitrogen. So it's a nitrogen with the plus. Let's make it huge, right? So there's nothing here, and yeah, that's it. So OH minus, you have the like oxygen with a negative sign, right? So because it gained an extra electron if you do the electron count. Okay, that's good. So we have blown through activity 1. So now what is next? So like we have, okay, so now it's a little bit kind of actually more interesting even, right? So water here, according to like Emily or like Emma, I think it was, right? So we were showing that the water behaved as an acid. Why was the water acid? So that's your example of the P, right? So because water technically lost H plus, right? That's what acids do. They lose H plus. So now let's take a look at our other acids, right? Which are carboxylic acids. It's a little bit more aligned with the organic chemistry nature. And we can try to tackle activity number 2, so which will kind of force you to review a little bit because we have here the carboxylic acid, right? So that was from the past, and then how they dissociate will also be kind of like highlighted here. So we have the butanoic acid and some secondary amine. So if somebody wants to give it a try, so like you can do that. So that is activity number 2. Okay, great. So yeah, we have the first candidate. Let's see what happens, right? So it's gonna be even drawn before me. So that's like one of your peers again. We'll show that. So everybody has a chance, hopefully. So yeah, just give it a try, right? So like, and then maybe you can like figure out for the second part of this activity. So let's see what happens. Carboxylic acid. So you have some nomenclature review, right? So it's going to be the butanoic acid. Yeah, that should be redrawn. So remember your functional groups, right? So that's now the review. So we didn't talk about this today. So, and now you made the correction. Great. Okay, so that's looking good. That's the butanoic acid reacting with some sort of secondary amine. Okay, that's a good secondary amine example. Nice and simple. So you just have a couple methyl groups. So that's fine, right? So you can make some more complicated. So it could be like diisopropyl amine as a secondary amine, right? So, and here you go. Okay, we made the what's it called, the anion from the acid. Good. So acid behaved as an acid by losing H plus, right? Amine behaved as a base by gaining H plus. So, and then here we go. Okay, great job. So I think it's all looking like perfect, basically. So some kind of like extra review, right? So like in terms of like Gen Chem, right? So, but this is going to be the time for the Gen Chem to show up. So we have the acid. Acid makes what? It makes this guy, right? So it makes the opposite with the word conjugate. So it makes the conjugate base. So it's going to be conjugate base, right? So because this thing, if you look at this, it can theoretically act as a base because O minus can accept H plus, right? Very legitimately. So if this was the base, right? So the amine is a base by itself, then it's going to make what? Conjugate acid will be produced. And then if you look at this compound, why is it an acid? Because it can donate H plus, right? So this H plus will be donated as a proton, right? So it cannot accept any more H plus. It will like, repel them rather. So, but it can lose H plus. Okay, so like we have that. Okay, that's good for this activity. And now we have the like ultimate tertiary amine and what else? And butanoic acid again. Okay, so let's so since I was saying that's the last lecture of the semester, so maybe some more new people would like to give it a try. So we have one candidate, that's good. And yeah, you can just go ahead. It's like Megan is gonna give it a step. All right. So we have you have color choices there. So let's see what happens, right? So some kind of like new situation on the block here. Butanoic acid, hopefully there is no extra H. Like
No, I crossed that.
Yeah, okay, good. So yeah, and then we have the tertiary amine. So okay, well, it's gonna be our triethylamine, or yeah, it's gonna be tripropylamine. Okay, good. So that is a nice example. You can use that, and then we'll see what happens, right? So again, if you draw that like with the carbons, don't forget the H's, which is what Megan is doing here. So good job. And our anion. Okay, good. So that looks like the bonds drawing helps, right? So you can also draw like orange bond theoretically to just show to yourself that this bond will be broken. Unless you know, then you know, right? So, and you also need to not forget N plus. It's going to be just put the plus charge on the nitrogen, right? So there's going to be a plus between the products, so that's fine. And then, yeah, you will have the charge. If you show a charge, that's a good point, actually. Yeah, all set. So then you can show it in the circle. So yeah, I think it's good. Yeah, it's fine. Yeah, all set. So yeah, charges are typically shown in the circle, not to confuse them between the fact that when you show the like two chemicals as products, you go like C plus D, right? So this is going to be just the addition of the chemicals in the mixture, and then these are charges, right? In circles are charges. Without circles, it is just kind of like A plus B, right, type of deal. So that's what that plus means. Okay, well done. So this is your again, same things, right? So literally the same thing was happening, right? In both cases, like in a row. So the bonds are broken, right? So this bond is broken, like OH is done, and then this lone pair participates in the bond formation. So then here you have acid, base, right? So then acid makes this one, right? So conjugate base, base. And then you go from the base to the conjugate acid. So conjugate acid, that's what will be made. All right, so that's good. Then what else? We have some kind of like, that's some more reactions right here that can be happening theoretically, right? So we now look at a little bit different acids, right? So such as like HCl. So what's going to happen here, right? So here you can see the proton transfer. So like same thing. So you break the HCl bond to produce H plus and Cl minus, right? So then you are going to make your like NH3 plus piece. just like it was shown in the past by your peers, right? So you're going to make the new NH bond. So the plus charge will be technically on nitrogen, but people kind of like draw it like that as well. So that happens sometimes. So, but you need to understand in this case that according to what we have just been discussing, right? So this plus in the purple circle will belong to the nitrogen, right? So, and then you go from NH2 neutral to NH3 positive. So since you also have the formation of the Cl minus anion, you are going to form a salt, right? So because you are going to have the like Cl minus anion, like imagine sodium chloride, for example, right? There is Na plus and Cl minus. So same here, right? You are going to have Cl minus, that's going to be your anion. And then you also happen to have the N nitrogen with a positive charge, right? So that's going to be kind of like an organic salt, right? So that is derived from amines. So even though technically it doesn't contain the metal, so people decided to call it a salt. So because it almost looks like your sodium chloride, right? Except instead of sodium plus, you have this kind of like nitrogen with a plus and like some crazy structure on it, right? So, but this compound happens to be like a water soluble, so just like salts do, and people decided to say, okay, well, let's just call it like a water soluble salt, right? So it's going to be your like amine hydrochloride. So why is it? Why does it matter? So because this compound can be used as a drug, as far as I know, right? So or like many amines, basically, or many drugs contain the amino group, right? So, and then oftentimes like organic compounds are not soluble in the water and not soluble in the human body because of this. So like people decided to kind of react them with the HCl, and then they make the salts, which are water soluble, which are compatible with the human body. And then you can kind of like cajole the drug into the bloodstream using like this approach, right? So just turn your like organic compound into the salt. And then, yeah, it's done just by means of the proton transfer reaction, and then the ions, the counter ions will associate, right? So theoretically, it could also happen in this case, right? So it's just kind of like more advanced thing, but here you literally have same situation. You have your N plus and an anion with a minus charge. So theoretically, it could also be like a salt, right? So because same principle will happen to be here as well, right? So you have the minus and positive charges interacting just like in the slide. All right, so then what else? So let's take a look at some more examples. That's just going to be your general example, how you can like react some sort of amine with HCl, and that's how you form the ammonium salt, right? So again, here, like what do we need to pay attention to? Like a couple things, right? So the, let's say, yellow electrons will be shared now, so they will make the NH bond. You are going to have the positive charge on the nitrogen, right? It's very close to the nitrogen. And you are going to have the Cl minus. So because, why? Because again, this bond will be broken, right? And then the green electron will go completely to the Cl, right? Or this like a pair of green electrons will move to chlorine completely. Chlorine, as a result, will get an extra electron and it will get the negative charge, right? So that's your kind of like Gen Chem foundation, basically. So just some more examples, right, with particular structures that we can kind of show. Like nothing changes except here we show explicitly the metal, but the bonding patterns and the charge patterns will remain the same. So now let's take a look at some kind of like maybe more examples here. So I don't know, like we did basically C, so maybe we can take a look at maybe like B, for example, right? So they're like very similar, or maybe let's do A, right? So A is finally the secondary amine here. What do I do here, right? So first of all, I need to notice the lone pair of electrons, right? So and the fact that I have HCl. So in which case I'm going to like make sure that H plus is produced, right, as a result. So, and then it will associate with my amine. So let's show it, show the result, right? So you're going to have nitrogen. So those things are redrawn. So hydrogen here, then the yellow electrons are shared. So you are going to have the new bond, right, between N and H. Okay, that's good. So then I'm going also to have the positive charge on nitrogen. So I can just remember that. And I must have Cl on the side, right? So that's my salt. So again, you have N plus, Cl minus, right? So those things will like repeat themselves in cases A and B, if you think about that. So then what else do I have? I have an NH bond, so in all cases as well. And yeah, that's it. So like my salt is produced, right? So pretty straightforward in this case. After we again like put down some kind of like get the hold of the foundational principles. All right, so let's see if we have the okay. So activity number 3, it's like about further chemical reactions of amines, right? So and then basically here, what we're gonna do is take a look at how the so-called amides are made, right? So previously told me that amides have the nitrogen in them. So and indeed they do, right? So if you look at the like amide group, it's going to be here, right? So that's going to be this combination of atoms, CON, right? So I'm saying CON because to the nitrogen, you can attach different things, right? So maybe it's going to be a couple H's on the nitrogen, right? Maybe you are going to switch one hydrogen to some kind of like alkyl chain, right? Maybe you are going to switch both hydrogens to something else, right? So, but still, you have the amide, which is going to be looking like that, right? So that's how we can describe it. So it must have the carbonyl, and carbonyl carbon is attached to the nitrogen, right? So that's your amide. So that's the combination of atoms that will lead to the amide versus amine. Amine is different, right? So we have just been looking at a bunch of amines. For example, they don't have the carbonyl group, right? So that's something to keep in mind. So just be careful when you kind of like circle or see the circled functional groups in the exam. So pay attention to like the immediate environment of the nitrogen atoms, right? So we can have also kind of a bunch of amide bonds in a molecule, right? So this is known as a peptide, for example, right? Peptides are known to have like a bunch of those amide bonds. Or if you see the amide bonds in peptides, such as maybe like, I don't know, like whatever you consume for the like gym purposes, right? So this will be called a peptide bond as well. So like, but it's nothing more than the amide linkage anyway, so that you can also see in polypeptides, right? So you have a peptide which maybe contains, let's say, 1,000 amide linkages. So then it's going to be polypeptide, right? Or polyamide from the like more chemical perspective. So anyway, so now let's take a look how those are formed, right? I think we're gonna actually get to the reactions right away. So how the amides are formed. So this is going to be kind of like the focus for our exam. So that's going to be amide synthesis, right? So another thing, so hydrogen bonding can also happen in amides, by the way. So here, let's take a look at that like real quick, right? So you have delta minus, delta plus in your amide, delta plus and delta minus. So if you want to show the hydrogen bonding in amides, it will happen, right? Because why? It has the NH bond, which is kind of like prerequisite for the hydrogen bonding. So we can say, well, amides can participate in the hydrogen bonding, right? So typically, we can show it with the water maybe, right? So like we can do that. Water has the OH bond, which is also prerequisite for the hydrogen bonding. So like it's a very nice coincidence. So then here, all we need to do is basically use our knowledge of the partial positive, partial negative charges, right? And then here you see it's drawn this way because you align delta minus on oxygen, delta plus on H. Okay, good. You can show the hydrogen bonding. So then you align delta plus on H from the amide, right? And then you align delta minus on the oxygen here, delta minus. This is delta plus. Okay, good. So they will attract. So that's your example of hydrogen bonding between the like amide molecule of some sort and the water molecule. Now, finally, to the synthesis, right? So here we again use our previously known compounds such as acid chloride. So that's why it was kind of like important from the past, because it can be used to make the CN bond, right? So here the reaction is pretty straightforward. You have like compound A, acid chloride of some sort, compound B, it is going to be your amine, which can donate or which can lose H, right? So that's going to be kind of like the key word here. So it must have the NH bond. So meaning for amide synthesis, you typically will use either primary or secondary amines because they will have the NH bond, at least one of them, right? So then the situation will be kind of like pretty simple. You are going to break Cl bond and an H bond, right? So as you can see, HCl will be combined, right? So into your side product, HCl. And then you're going to make a new bond, right? So which is going to be a red electron from carbon, a red electron from nitrogen. So they will make this kind of like red CN bond. That's the amide. You have carbonyl, you have CN bond. You made the amide just now. All right, so now let's take a look at some kind of like specific examples, right? So because there again, we only are going to recognize the common pattern, right? So here I'm going to, I think my laptop just, okay, laptop is still functional, so, but I need to make a switch. Hold in there, please. Okay, presentations. Okay. Okay, so where was it? Okay, so we are at the amide formation already, and so it's pretty good. So here we go. So let's take a look at some examples, right? So this is going to be our example for the amide synthesis, right? So we make the CN bond. So another option to make amides will be to look at the examples. Okay, so do we have here any good examples? We do. Let's take a look at like the ultimate example here for the amide formation, just one more. So you have this case, right? So when you have the like cycle COCl. So in this case, we are going to have the secondary amine, right? Technically, right? You have nitrogen with the methyl here, but you also have H. So what do we need to do here? So that's all we need to do basically. Notice H and Cl, right? So that's what you're going to hunt for when you make amides in like various other examples. And now here, so like electron, like big yellow dots, right? So what are we gonna make here? Okay, well, let's redraw a lot of stuff, right? So this is redrawn. So you have carbonyl, oxygen, right? So then here you have nitrogen. So nitrogen still retains the methyl. So this is going to be the methyl in this brown circle, right? So now the only thing that will happen is the new bond, right? So that's going to be your green bond right here. So this will lead to the amide formation. So even though I look at this like relatively complicated case, I still see, okay, well, H and Cl can be released. So consequently, the kind of like free electron on carbon will combine with the free electron on nitrogen. They will make the amide bond. So that's where we are going to be. And at this point, we are done because my iPad unfortunately died. So, but if you participated in the extra credit activities, you can stop by to put down your name and we'll be all set. All right. So, bye everyone.